Hi everyone, my name is Ryan Carl, and I want to thank all of you for attending our talk on our recent paper entitled Cryptonomial, a framework for private time series polynomial calculations. Without further ado, let's begin. As many of you know, in modern times, the ability for a third party to conduct a form of data analysis on a group of users' private records is becoming more and more important for a variety of business and/or research tasks. However, the data that many scientists would like to run these data analysis algorithms over often contains sensitive private information about users, specifically about their health, such that its publication could damage their privacy in a serious manner. Especially in light of the COVID-19 crisis, there is a renewed interest in being able to apply rigorous data-driven analysis to support real-time disease detection and diagnosis, specifically with common forms of machine learning, such as linear regression, support vector machines, etc. Something that many of these algorithms have in common is they can be modeled as multivariate polynomial calculations, which has motivated this work. So, given the current state of affairs, we are very motivated to solve this particular, more formalized problem. We would like to let a set of users, we denote S, be able to privately compute some polynomial function over a collected set of their time series data. We would like them to be able to send their data in some encrypted form to some untrusted aggregator who will perform the computation such that although the aggregator can learn the final result, they are not able to learn any individual honest user's data in the plain text form. Now, more specifically, we'd like to support a polynomial evaluation of a general multivariate polynomial modeled in the following equation, where z is the number of product terms in the polynomial, c, j, and e sub I, j are the public parameters for the polynomial, and the m is the secret data for individual users at a particular timestamp, which we denote ts. Over the course of our investigations, we were able to develop what we've named Cryptonomial, which is a new framework to support for the first time ever private stream aggregation, or PSA-based general stream polynomial evaluation. Although this is a framework, we did develop an instantiated protocol, and in our paper provide a formal proof of security for the protocol, guaranteeing that it protects users' privacy. We also developed our protocol, and our experiments demonstrate that it offers improved efficiency over existing work by sometimes orders of magnitude. Before we discuss in more detail our framework and our protocol, you might think there's other techniques available that could also be used to solve private stream polynomial aggregation, and that would be true. However, a lot of these techniques are ill-suited to efficiently provide a solution to private stream polynomial evaluation. For instance, although you could use fully homomorphic encryption, this technique has very high computational overhead, which makes it impractical. Another technique you could use is differential privacy. However, using differential privacy would introduce noise that would negatively impact the overall accuracy of any data analysis performed. Another technique you could use is secure multi-party computation. However, naively applying this technique would dramatically increase the communication overhead of the protocol and make it impractical to be deployed in the wild. Private stream aggregation comes closer, and it is very efficient. However, it's only limited to computing simple functions. However, as you'll see, we use this as a building block when developing our own protocol. There are some other existing techniques that you could perhaps use, such as oblivious polynomial evaluation. However, this is only focused on the two-party setting, whereas we would like to support a large number of individual users. Related to this technique is privacy-preserving polynomial evaluation, which would solve this problem, but has very high communication complexity, which might make it impractical in the real world. So there's a lot of techniques out there, but not all of them are well suited to solving this problem. However, as I mentioned, PSA comes the closest. As a brief refresher, for those of you who may not be familiar, PSA, or private string aggregation, is a protocol that seeks to let an aggregator compute a sum calculation of a set of users, we'll say n users, private inputs x, for a particular timestamp, which we'll call TS. All of the users, as you see in the diagram, encrypt their private input x using some encryption function in a special manner such that when all of these ciphertexts are sent to some aggregator, the aggregator can sum all of the ciphertexts such that the plaintext sum is recovered, but the aggregator is not able to learn the individual input of an honest user. They only learn the final result sum. Now, although PSA is a really nice, efficient protocol for computing a sum, it's clearly quite challenging to easily adapt PSA to support a polynomial function because PSA only supports either a sum or a product, but you can't combine both together naively. There is an existing paper by Zheng that uses pure cryptography, but to do this it incurs high levels of additional computation that negatively impact its overall performance. What we are able to do is take a different approach and compute some operations inside of a trusted execution environment, specifically IntelSGX. IntelSGX is described in more detail in the paper, but for the purposes of this presentation, it's safe to know that it's just a set of new CPU instructions that can be used by an application to set aside private regions of code and data. The figure illustrates what this looks like at a high level. Essentially, an application can be launched on a platform and using the new CPU instructions can create an enclave. Later, the application can call a trusted function to send data into the enclave. Once the data is inside the enclave, it cannot be tampered with or modified or eavesdropped on by malicious software running at a higher privilege level. Once enclave-based computation is finished, we can return to the main execution of the program. Importantly, an external user can verify that a platform such as the aggregator is running IntelSGX in a cryptographically secure way, and that their data, if sent into the IntelSGX, will be kept safe. The last technique that we need in order to build our cryptonomial framework is the complex canonical embedding. This is a well-known algorithm from the field of lattice-based private stream aggregation that allows you to transform a complex number into a polynomial and then later reverse the process. We use this in our protocol to transform floating point numbers into polynomials in the lattice space. Later, we can undo this operation to recover those floating point numbers. So together with lattice-based PSA, the CCE, and the TEE, we can build Cryptonomial. A deep discussion of lattice-based cryptography is out of the scope of this presentation, but we do know enough to now be able to appreciate a sketch of our idea. Essentially, for our idea for Cryptonomial, we have all the users first take the natural log of their plaintext input. Once this is done, their input is a floating point number, so they can use the CCE to encode their input into a polynomial to maintain numerical stability when using logarithmic operations. Once this is done, they can encrypt their input and send it to the aggregator. Once the aggregator has all of these inputs, they can compute the sum of them inside of the TEE and later take the exponential over this. Now, it's a well-known fact that these operations will produce the product of all of the plain text values. Once we have this product, we can sum up all of the products in the polynomial to compute the final polynomial function output. This figure summarizes our framework for a private string aggregation of complex numbers. Essentially, if there's a group of users that have time series complex input, they can apply the CCE to map it to time series integers. Once this step is completed, they can use any private stream aggregation algorithm to compute on the aggregator's end the additive aggregation of the time series integer output. Once this is complete, we can take the inverse of the CCE algorithm to compute the final output, which is the additive aggregation of the complex numbers. We actually can use the framework discussed on the previous slide as a building block for our larger Cryptonomial framework to support secure polynomial function evaluation with any PSA. Essentially, all the users have their own individual private time series complex input from before, but before they feed it into the prior framework, they first take the natural logarithm of their input. After they've done this and fed it through the framework on the aggregator's end, this intermediate result is sent into the TEE. Once inside, the TEE can use the final key for the additive aggregation to compute the intermediate value. If we did this outside of the TEE, it would be a security vulnerability, as a malicious aggregator could potentially learn an individual user's private input. And this is why this must be done inside a secure trusted hardware environment. Once this is completed, we can simply take the exponentiation of that result to recover the multiplicative aggregation terms for our polynomial. Once we have all the terms, we can simply sum them up and output from the TEE the final polynomial function output. Here we include a quick toy example to help illustrate how this protocol works. Assuming we have 3 users that want to compute a polynomial function, what they would do is they have their private message M. First, they would take the natural log, then they would take the complex canonical embedding of that intermediate value, and then lastly they would encrypt that result using the PSA secret key provided to them. Once this is done, they send their ciphertexts to the aggregator, who first computes the sum of the ciphertexts outside of the IntelSGX. They then send this temporary value into the enclave, which can be decrypted using the aggregator's secret key. Once this is done, they can take the inverse of the complex canonical embedding and later take the exponential of that intermediate value to recover the final product. Once this is done, they can compute the sum over these products to determine the final output result y, which is output from the TEE to the aggregator in a plain text format. We can now discuss some of the mathematics involved in our protocol. For the purposes of this discussion, we reference the BGV lattice-based crypto system because it is relatively well known within the cryptography community. However, note that we could use any lattice-based crypto system that is amenable to the complex canonical embedding to instantiate our protocol. Our protocol consists of 3 steps, the first of which is the setup step. During setup, all of the users are given their secret keys K. These secret keys K are generated in a special way such that when they are added together, they all sum to 0. Because we're working with BGV, all of these Ks would actually be ring elements in some quotient ring of polynomials. Okay, so once setup is done, we would move to the encrypt phase of the protocol. This happens on the user's end, and the users, with their private input M, would encrypt their data after first taking the natural log of their private plaintext data and then computing the complex canonical embedding over their plaintext data. This encryption over this value is computed using this formula inspired by BGV. Essentially, it involves using a pseudorandom function, or PRF, computed over some timestamp S, along with the secret key K, and it also involves using some standard crypto parameters from the BGV scheme, such as T and Q, to help mask this plaintext value using the noise term E. Once this is done, the users send their ciphertexts to the aggregator, and the aggregator can compute an intermediate result, which we call Y sub S for the given timestamp S, by summing up all of these intermediate ciphertexts and taking mod Q, the result. Once this is done, they can send Y sub S into the IntelSGX enclave, where the aggregator's own private key is stored. The private key takes the form of the PRF of the timestamp times the aggregator's secret key, which is kept hidden from them inside of the TEE IntelSGX enclave. Once this is done, we compute the sum to recover the sum of the complex canonical embedding of the natural log of the inputs. Once this is done, we can use our trick from before, where we use the exponential to recover the plain text and remove the natural log, after first having taken the inverse of the complex canonical embedding. This sequence of steps allows us to recover a product term. If our polynomial function has multiple product terms, we would have to sum up these individual product terms inside of the enclave before outputting the final function output result in the plain text form to the aggregator. Beyond creating the Cryptonomial framework, we also instantiated our protocol to run some experiments and see how fast it would be in the real world. We simulated running our scheme using C++11 and version 2.10 of the IntelSGX software developer kit. We ran experiments on a computer running Ubuntu with an Intel Xeon CPU. We used the SLAP library as our lattice cryptography backend when computing, and we used linear regression as a case study task to compare the efficiency of our protocol to the existing work of Zheng. First, we took some benchmark measurements to see how well our protocol scales as we increase the number of users, and we can see it scales at a relatively linear rate, which we find promising. Later, we computed a linear regression over data taken from the UCI machine learning dataset database, and we compared the running time of our protocol to the existing work of Zheng, which is known as PDA. As you can see, in situations where there's large numbers of records, our protocol is very efficient over existing work, sometimes even multiple orders of magnitude faster. This makes sense because, whereas the existing work of Zheng relies exclusively on expensive cryptographic primitives to ensure user privacy, we outsource some computation into the TEE, which is more efficient and allows us to save running time costs. So, in summary, with our Cryptonomial paper, we first developed a new framework to support for the first time PSA-based general stream polynomial evaluation. Also within the paper, we provide a formal proof of security for our instantiated protocol to guarantee privacy for users. Lastly, we also perform some experiments to verify the improved efficiency of our protocol over existing work. Thank you for listening, and this concludes our presentation.